everyone. I want to go over a problem which is about rocks sliding in a bowl. Sliding is important because we're not going to roll or anything. So in this problem, we have a situation where we've got a hemispherical bowl. See how good this is, all right. And we've got a rock that is going to be sliding from point A down to point B, which is here at the bottom. Okay, now we can sit and think about this for a minute of what's going on with our rock. But it's going to start from rest, so that means that our initial velocity is 0. And at the end here, it's going to have some velocity that's going to be moving in that direction. Okay, we're given a couple pieces of information that the rock is small compared to the radius of the bowl. So the radius of the bowl gives us a hint that it is well, it's hemispherical. So it means that it's a circle, right? It's a sphere here that we're looking at. So it's a constant R all the way around. And we're going to analyze the friction that's going to be happening while this rock is moving. So it's some interesting pieces here that we're going to think about. So the first question asks for the pieces of what's going on between points A and B. And so we're going to do a couple of things. We're going to, I don't want to type, right? There we go. We're going to do a free body diagram of this rock between points A and B. So here's our free body diagram. And at some point, let's take it right here. At some point between A and B, we have the rock moving, right? It's accelerating because of gravity. So we have gravity acting down. So we'll call that our mg, where m is the weight of, or the m is the mass of the rock. G is our acceleration due to gravity. We have a normal force that is perpendicular to the surface of the bowl, and we have friction, and that friction goes against the motion of the rock. And so if we are accelerating down in this direction at this particular point, then we have the force of the rock going against that. So so this is the free body diagram. Now let's look at this a little bit closer, or specifically about the force of gravity. So here's our normal, here's our frictional force, and it's a kinetic friction because we're sliding, right? It's a sliding motion. And here's our gravity, our force due to gravity. Now, the important thing here is that we can now define at this particular point, right, we can define our axes, our coordinates, with a positive y and a positive x. So that puts the acceleration at this point all in x, and it allows us to then divide up the pieces of gravity specifically, right? So we can have a piece of gravity in the y direction and a piece of gravity in the x direction. And so this allows us to now analyze what is going on with the rock, what's causing it to move from a force standpoint, right? So what's causing it to accelerate in this direction is this x component of gravity that is counteracted a little bit by the friction. And so that gives us a sense of what is going on with this rock. Now, for part A, we want to find how much work is done on the rock by the normal force and by gravity. Okay, so we need to think about, so let's come over here, let's start A. So we want to find the work done on the rock by the normal force and the work done on the rock by gravity. Let's think about this for a minute. If we want to identify the work done by gravity, done by the normal force, for instance, work is defined as whatever force we're talking about, dotted, and that's a vector, dotted with the s vector, the displacement vector, the vector that shows the direction of its motion. Okay, so in particular, we're looking at the normal force dotted with the s vector. Okay, at this particular point, this point in time that we've chosen, what direction is the s vector? Specifically, it's in the same direction as our A, right? But that changes as we go down because it is circular, so it's going to adjust and change. But guess what also is adjusting and changing? The n, right? So let's say we pick a point here. We have an n that comes out, and we have an s that looks like this, right? No matter where we pick at this point, we have n that comes out that is perpendicular to the surface, and s that is perpendicular to it. So no matter where it is, we see that n is perpendicular to s. And so if that is the case, then we can write the magnitude of n, whatever that may be, times the magnitude of s, whatever that may be, times the cosine of the angle between them. And that angle between them is 90 degrees, which means that the work done by the normal force is just 0. Okay, now we want to look at the work done by gravity. So this, we're going to look at, again, the particular force and the S. Now, another way that we can write this is to look at the force that is parallel to S, or to look at the magnitude of the S that is parallel to F. So for our force of gravity work, it is most convenient to talk about the S that is parallel to the force of gravity, because, oh, I guess I should write this. This is gravity here. Because gravity is not changing, right? The S is changing, but gravity is not changing. And so then the question is, well, what is the total distance that is parallel to mg across this rock's motion? And that distance is this height change, which is r, the radius of the circle. So it goes from some initial point up here to some point here at the base, and that change, that S, or that S parallel to the force of gravity is what we can multiply here together. And so we have that the force of gravity, which is mg, times the parallel, oh, I lost my cursor, parallel distance of S is r, and that becomes the work done by the force of gravity. Now that should start to look a little familiar, because we can do a couple of things, right? So this is using our work and our free body diagrams to solve this problem, but we can also use energy conservation. So let's look at energy conservation here. I guess I'll also say, right? So, well, our energy conservation, we'll write out, and that'll lead us to our next kind of pieces. So energy conservation, this tells us that whatever energy we start with, we have to have it at the end. Now it can change form, but the total amount has to be the same. So here, at our initial position, we can have some kinetic energy. We could have some initial gravitational potential energy. We could have some initial elastic potential energy, so that'd be like a spring. And we can have some other outside forces, which in this case is friction that we're going to have to be dealing with. And then at some endpoint, we have some kinetic energy, we have some final gravitational potential energy, and we have some final elastic potential energy. In this case, we don't have any springs, so these are all going to go to zero. We don't care about any springs in this problem. So now what I'd like to do is write under here the information that we know. So what is our initial kinetic energy? Kinetic energy is written as 1/2 mv0 squared, but we know that our initial velocity is 0, so we can write that the initial kinetic energy is 0 because our initial velocity is 0. We can also then analyze what's going on with our initial gravitational potential energy, which is just mgy0. We can identify this y0 as being our initial height. So if our y0 is our distance r, that means that we are defining then this base, or when we get to point B, our final, as our 0. And we're allowed to put that 0 wherever we want. In this case, we'll put it at B because it's nice and convenient. We do that a lot in physics, make convenient things. So, because it makes our lives easier. So then that means that our not what I wanted, right? That means that our initial potential energy is just mgr. Okay? And we'll talk about our work other, but this work other is what we're going to have for our work of friction. And specifically, it's going to be less than 0, which means it's going to be removing energy from our mechanical energy, its motion, to some thermal, right? It's going to transfer it into that. All right, so now we can look at what's going on our final side. So on our final side, we have our kinetic energy, which is our 1/2 mv final squared. So that's the speed that the rock has at the bottom of the bowl. We have our gravitational potential energy, which is our mgy final, but because we've set that y final to be 0, then this is just 0 because our y final is equal to 0. And as we already stated, our elastic potential energy is just 0 because we don't have any of that, so we're not going to worry about that. Let's see, there we go. All right, so that means that we can rewrite this whole thing into a 0 for our initial kinetic energy, mgr for our initial potential energy, our work done by kinetic friction. And that's all equal to our 1/2 mv final squared. And adding that to a potential energy of 0, so that we just have mgr plus work done by friction is equal to 1/2 mv final squared. Ta-da! Okay, so now this is allowing us to look and see what is happening in terms of the energy and the forces, right? It gives us a relationship between our potential energy, which we got. Notice that this mgr is the same work that gravity does, right? And that's how we can derive and define the gravitational potential energy. So that's nice to see. Then we have this 1/2 mv squared, which is the final kinetic energy of the system. Okay, so luckily we're given some of this information in order for us to find what we're looking for in part B, which I actually didn't explicitly state, so I'll do that now. Whoops, there we go. For B, we are looking for the final velocity. At the end of the problem here, it states the things that we know, and we are given that the mass is 0.20 kilograms. We're given that the radius is 0.5, which is good because we needed this information to find A. And then we're given that F is the work. That's kind of a bad way to write that. We should have, or it should have been given as the work of friction. There we go. Is 0.22 joules. So this is the amount of work that friction does on the rock as it moves down. So now, if we look at our piece over here, our equation for energy, we have M. We know what G is. That's our 9.8 meters per second squared. We have R. We have the work done by kinetic friction. We know what a half is. We know M. And so now the only thing we don't know is our final velocity. So now we can solve for that. So that our final velocity is equal to the quantity 2 mgr plus 2 times the work of kinetic friction divided by m, because that m should go away. And we take the square root, and that's what we get. And so we can plug those numbers in, or those values in, to get our final velocity here. That's good. That helps us identify what's going on. So we can look at this and see that the final velocity, oh, darn it. I'm missing something. Can you identify what it is that I forgot to do? I forgot to turn this positive sign, right? Because this is, I was gonna put that value in, but I'll do it right now just so you can see it. Right? So we know that the work of friction is removing energy from our motion, and so this has to be a negative value. So we just have to be careful. If you include the negative in the in your value, right, over here, if we put the negative over here, and that would have been fine if we had a negative in there. But I stated here that it was going to be less than 0, so that's why I didn't have the negative in there. But just to make it more clear about what's going on, then I'll put the negative right there for you. So the work that the friction is doing is removing energy from being transferred from the potential energy to the kinetic energy, and so it's going to make this a slower velocity, right? If friction wasn't there, then the velocity would be greater. So then now let's answer these next few questions. Of the 3 forces acting on the rocks that slides down the bowl, which are constant and which are not? So here's our 3 forces. We have friction, we have the normal force, and we have the force of gravity. So we can look at this and analyze what each of these are doing. Okay. So what happens? So in order to do that, we need to look at the sums of forces. So let's get the right color up here. So we need to do a sum of forces acting on our rock. And we need to do that in terms of x and y. So in the x direction, we have some frictional force acting in the negative x direction. We have a piece of gravity acting in the x direction, and that's causing the acceleration. In the y direction, we have n, the normal force, and we have some component of gravity, and our acceleration is equal to 0. So that tells us that our n is equal to m times gy. Okay. So the question that we have to think about then is, what is happening to each of these forces? So let's look at mg. Is mg constant as the rock slides down the bowl? And the answer is yes. It doesn't matter where the rock is at point A or point B, mg, the force, is the same. It's not changing direction. It's always down. And it's always the same value. That height difference doesn't matter in this case, okay? And so that force is constant. So we'll say that mg is one of our constant ones. Now let's look at the other ones. Force of friction. Let's rewrite this equation to be in terms of friction. So friction, Fk, or F sub k, is equal to m, or the x component of g minus m times the acceleration in the x direction. That looks like a y, that's an x. Now, we know what is happening to our friction in that it is always opposing the motion. But we also have to note that this mgx changes as we go around this sphere, right? So when the rock is at the top, the mg is completely in the x direction, right? There's essentially no y component, or no component that's perpendicular to its surface. But as we go down and move closer and closer to point B, then all of a sudden, the mg has transferred from the x direction to up and down, vertical, in our y direction. And what I'm meaning is that we're changing our coordinate system here a bit. So at the top, we have something that looks like this. And at the bottom, we have something that looks like this. All right, so we're analyzing everything as the rock is moving down and around the sphere. And so our components are changing, which means that we can also then look over here at the n, and that means that we have our component of our component of gravity in the y direction that is also changing. It starts out very small, and then it gets bigger and bigger. So as we go from A to B, the y component of force of gravity goes from essentially 0 to some max, which means that n goes from some 0 to some maximum value. So that means our n is changing. So that means that it is not constant. We go over here and talk about our force of friction. If our mgx is going from some maximum value to some minimum value, which is the opposite of over here with our mgy, then that means that this is going to be changing, right? And our frictional force is also dependent on n. And if n is changing, then that means that the frictional force is changing. So it is not constant either, right? Because we know our frictional force is also defined as mu k n. So if our n is changing, then that means our frictional force is changing. So the only force that is constant throughout this whole thing is force of gravity. And again, we're talking about forces, not about energies, not about the work, right? So just remember to make that distinction. Okay, last piece for part D. We want to find the normal force at the bottom of the bowl. Okay, so let's write this over here. This is our last piece. What is n at point B? So let's draw a free body diagram at this point. So at point B, we have the normal force, which is directed upward. We have gravity, which is directly downward. We have a velocity that is in this direction. And because it is a circle, that means that the acceleration at this point is now what? It means that our acceleration is now in this direction, which means the acceleration is all in a perpendicular direction, which means that it is going to allow us to write that the sum of forces in the y direction at this point is equal to mv squared over r. And the sums of those forces are N minus mg is equal to mv squared over r, which means that the normal force at point B, I guess I should write that up here too, is equal to m times the quantity v squared over r plus g. And we use the velocity that we got from our previous point down here in order to calculate that normal force. And so you can think about this in terms of, right, so we're adding these accelerations together, and adding that together means that we have a greater normal force. So that'd be like if you're in an elevator and you're standing on a scale, that the scale is a measure of the normal force. And so if the elevator is moving down and it comes to a stop, if you watch your weight, it hops up, it increases. If you're driving in a car and you're going over some bumps, when you reach the bottom of that bump, which is like the rock reaching the bottom of this bowl, you feel a greater force pushing up on you, and that is the effect of this circular rotational motion. Okay, so hopefully that helps and explains a bit, but this is another great problem because it combines our understanding of what work is with our understanding of energy conservation and putting all of these pieces together. So it's even though it is a very long problem, it is a very good comprehensive problem to really understand what's going on with all of the different pieces and how all of these pieces are acting together to describe how the forces are acting on an object. So I hope that helps.